Welcome. In this presentation and the next one, we're going to delve into one of the deepest mysteries in all of science, and that is what is the source of nuclear energy? Where does nuclear energy really come from? And you may have a little bit of a feel for that, but I'm guessing you don't really know a lot of the details, and they're fascinating, and I hope you'll enjoy learning about them. Here's how we're going to structure things over the next two presentations. So in this video, we're going to talk about the first bullet point here, the forces, the nature of the forces in an atomic nucleus. In the next two videos, I'll describe in more detail where the nuclear energy comes from and how that relates to some of the contributions that Einstein made to physics. And then I'll kind of set things up for an investigation that you guys will be conducting starting Tuesday this week. Okay, so now before we get going, unless you have each of these three items on your, at the ready, I want you to pause the video and make sure that you have these three items. Okay. All right. So make sure you're ready to take some notes. Okay. So first, let's talk about just to kind of set things up. Here I have an illustration of a helium atom. Okay, and specifically, it's the helium-4 isotope. So it's the variety of helium that has 2 neutrons and 2 protons. Of course, we remember that the protons are positively charged, and so we have 2 positively charged protons in direct contact in the nucleus. Now the question is, well, first of all, of course we remember that like charges repel. And if that's the case, then the question, I don't know if you've ever wondered this to yourself, but, what in the world is keeping that nucleus together? Why aren't the protons flying apart from each other? And to answer that question, we've got to talk about the fundamental forces of the universe. There are 4 fundamental forces. One is gravity, which we're all very much aware of. The second one is called electromagnetism, and this is the force that accounts for positive charge, negative charge, like charges repel, opposite charges attract, and also magnetism. But I'll bet you probably have not heard of the other 2 fundamental forces. One is called the strong force, and that's the force that we're going to be talking about here, and that's kind of the source. It helps explain the enormous energy that can be derived from atomic nuclei. And so if you're wondering what's the fourth force, well, if there's a strong force, there's got to be a weak force. And the weak force is what's responsible for radioactivity. So when particles are ejected from a radioactive nucleus, the weak force is responsible for that kind of radioactivity. Okay, so we're going to focus on the strong force right now. Now, first, I would like you to pause. Please push pause on the video, and I'd like you to carefully read this excerpt. Okay, so this, I hope, kind of sets the groundwork. Now here's another excerpt of text, and this is from Wikipedia, obviously, and I'd like you to pause one more time and read through this. Okay, now I've redacted one line of this paragraph because I don't want to give away a surprise that's coming in the next video. But I think you can see from these last 2 text excerpts that the nuclear force is that's where the energy comes from, that we use in nuclear power and nuclear weapons, and it's an incredibly powerful and attractive force between nucleons, but it only operates at very, very short distances. So as it says here, at distances of about 1 femtometer between their centers. One way to think about that, a femtometer is much smaller than a nanometer, and you can think about it in terms of the diameter of a proton or a neutron. A femtometer is about 1.5 to 2 diameters of a proton or neutron. All right, so you've got to get them pretty darn close together before they start to feel the strong force. Okay, so let me give you an illustration. All right, so let's say we are, we're playing Master of the Universe, and we're trying to create a helium atom, and specifically an atom of helium-4. All right, so we got the two neutrons together. We put those together, and that's no problem, right? Because they are neutral. There's no electrostatic repulsion going on between them. You can just put them right together, and they do not complain. But then you've got to get these two protons together. All right, they have to join the neutrons in the nucleus. But the problem is obviously they're going to start repelling each other, right? Like charges repel, and so this little lightning bolt is just to symbolize the repulsion. And let's say at this distance apart, my symbol for electromagnetic force is EM. So let's say that the electromagnetic repulsion at this distance is about this much. Okay, I'm going to use a little bar graph here to visualize the strength of the repulsion. All right, now at this distance, the strong force is also beginning to be felt, but it's very, very minimal at this distance. They're just not close enough together in order for them to be significant. However, as we move the protons closer together, you can see what's happening. The repulsive force from electromagnetism is getting stronger, and the weak force is getting a little bit stronger, but it's still not that big. We move them a little bit closer still, you can see what's happening to both, and now you can see that the protons they're about within 2 diameters of each other, and now the strong force is just about as big as the electromagnetic repulsion. The strong force is attractive. The electromagnetic repulsion is, like the name implies, repulsive. So we're just about at a tipping point, and when you get them close enough, the strong force really goes into effect, and it completely overpowers the repulsion from the electromagnetic force. And when you get them close enough, they snap together, and then it becomes very, very difficult to get them apart again. Okay, so this is why atoms that have more than one proton in the nucleus, that's why they stay together. It's because of the strong force. And if it weren't for the strong force, you could never get these protons to live together in the same atom. Okay, so that's part 1. In the next video, we're going to talk now a little bit more, in a lot more detail actually, about nuclear energy and how that fits into what Einstein did. Okay, so I'll see you there.